Okay, now let's discuss some previous year questions quickly so that you are all well prepared to go to the exam with full confidence tomorrow. Okay, why there is a need to establish the connection before the transmission of message? Briefly write the advantages and limitations of connection oriented protocol. So you're going to write about TCP, right? So why there's a need to establish a connection so that the other party knows that packets on this channel are going to come. It needs to reorder those packets. If they come out of order, it needs to discard duplicate packets. It has to kind of put those packets in order and send them as a stream of bytes to the other protocol at the upper layer, right? So it needs to do all of these things. And that is the reason why a connection is needed. The advantages are you can get reliability because out of order packets will be reordered, duplicate packets will be discarded, some amount of error checking is done. You also get flow control, congestion control, all of the various things that TCP gives you over UDP. And limitation should be it is slower to set up a connection. So if you want to instantly send something to a different party, then you cannot do that without first setting up a connection. And yeah, that would be one of its major disadvantages. Distinguish between CSMA CD and CSMA CA. Well, CSMA is for carrier sense multiple access, CD is for collision detection, and CA is for collision avoidance. So there you go, it's in the name. In CD, we let collisions happen, but we detect them when they happen. In CA, we try to, first of all, avoid collisions from happening. CSMA CD is usually used in wired Ethernets, and CSMA CA is usually used in wireless physical layer media. Though we don't have CSMA CA as part of the syllabus, so you can choose to ignore this if you want to. What's the need of UDP? So UDP gives us connectionless way of transferring data, right? So it is not always necessary to set up a connection, and this is usually the case for real-time applications like voice and video, where loss of data is tolerated to a certain extent, and in TCP that is not. So if you're trying to speak to somebody, if a few packets go out of order or a few packets get dropped, the human brain can still understand that, okay, they were probably trying to say this. But in TCP, you will have huge pauses in between because retransmission would be attempted, and that is not good for real-time applications. Would it not have been enough to just let user processors send raw IP packets? Yes, I mean, they can send IP packets, but you cannot do demultiplexing on the other end. I mean, it is not necessary that only one application in a host is using UDP. There can be multiple applications in a host that use UDP. So you at least need port numbers. So each UDP application would be given a unique port number in a host. Whereas if you just use raw IP packets, that is not possible because IP packets do not have port numbers. They just have the single source IP. And so you cannot use multiple applications if you end up sending just raw IP packets instead of UDP packets. Explain a way to do reassembly of IP fragments at the destination. So at the destination, all of these fragments can be identified as being fragments of this one big IP packet by looking at the ID, right? If the ID is the same, the identification number is the same, then they all will be deemed to belong to this one big IP packet, and reassembly will be done with the help of fragmentation offsets. So the packets will be ordered in increasing order of fragmentation offsets, and any holes will be plugged, right? So you take the fragmentation offset and you also have the total length, and you keep adding them for all the packets and make sure that you have one continuous stream of data, and you need to have the last packet, and you know that the last packet has arrived when you get a packet where the more fragments flag is set to 0. So that means there are no more fragments coming after that packet, right? That is where you stop. So if you have all of these packets in sequence and there are no holes, and you can do that by looking at the fragmentation offset and the total length, and you also need to know which is the last packet, and you will look at the more fragments flag. And if that is 0, that you have the last packet, and this is how you can reassemble IP fragments at the destination. With non-persistent connections between browser and origin server, is it possible for a single TCP segment to carry two distinct HTTP request messages? Explain your answer. No. I mean, let it be persistent or non-persistent, doesn't matter. In a single TCP segment, you can only have one HTTP request message. It doesn't matter whether it is persistent or non-persistent. In persistent connections, you can have a single TCP connection carrying different requests, but it's a single TCP connection, not a single TCP segment. A single TCP segment is going to contain one HTTP message inside that, and that one HTTP message is going to be fit inside one TCP segment. That's all. You cannot have two HTTP messages going inside one TCP segment. That's what I'm trying to tell you here. Okay. All of these pages are kind of laid out in a weird way because that's how they have scanned the document. Okay. What is the use of subnet mask in IP addressing? Well, you need the subnet mask to be able to figure out the network part of an IP address. So if you get a packet where the destination IP address is there and you want to know to which network this destination IP address belongs to, you take the IP address and then apply the mask. And in a mask where if it's a /29 address, so you'll have 29 ones from the left and then you will have just 3 zeros on the right. So you take this mask, write it in the binary form, and you write the IP address in the binary form and you AND the bits, corresponding bits. So what is left over, the result of the AND operation will be the network address. And then from that you will know, okay, this packet belongs to this network. That is the use of subnet mask in IP addressing. Let the size of congestion window of a TCP connection be 32 kilobytes when a timeout occurs. The round trip time of the connection is 100 millisecond and the maximum segment size is 2 KB. Find the time taken in milliseconds by the TCP connection to get back to 32 KB congestion window. Okay, so in Tahoe, what happens is that when there's a timeout, it goes to the slow start phase in which the slow start threshold is set to the current congestion window divided by 2. And the current congestion window here is 32 KB divided by 2, which is 16, right? 16 MSS because one MSS is 2 KB. So the current congestion window size is 16. And now the SS threshold will become 8, which is 16 by 2. And CWND will become 1 because a timeout has happened. Now in the next RTT, it will go from 1 to 2, right? You keep counting the RTTs. I'm not going to write anything. I'm just going to give you the idea of how to solve this. In the next RTT, it will go from 2 to 4. In the next RTT, it goes from 4 to 8. At that point, it matches the threshold, the SS threshold, and it goes to congestion avoidance, right? Additive increase. From 8, it takes one round trip time to become 9. Another one to go from 9 to 10, then another one to go from 10 to 11, 12, 13, 14, 15, 16. It's going to take like 5, 6 more RTTs to go from 10 to 16, right? So, and we can actually count it. One RTT to go from 1 to 2, another one to go from 2 to 4, another one to go from 4 to 8, then 8 to 9, 9 to 10, 10 to 11, 11 to 12, 12 to 13, 13 to 14, 14 to 15, 15 to 16. So I might be wrong, but I can see this taking 11 RTTs. I mean, your answer might be different. I am just doing this without writing anything. So yeah, about 11 RTTs is what it will take. So it can take 11 and multiply that with 100 millisecond. That's a round trip time given here. So you'll be getting around 1100 milliseconds. That's the answer. Difference between stop and wait, go back and selective repeat. And you can do this very, very easily. There are detailed videos about this, stop and wait, just a single bit sequence number, 0101, go back and, well, you can have sequence numbers go from 0 to some power of 2 minus 1, and the window size can also be bigger, right? But here in go back and you cannot do out of order acceptance. If you are stuck somewhere, then you will be rejecting the future packets. And only when a timeout occurs, you get that packet, then you move forward. But in selective repeat, you keep everything. And in go back end, the acknowledgement number contains the next expected sequence number. But in selective repeat, you send the acknowledgement number for the exact sequence numbers packet you end up accepting, right? Some of the differences, you can write even more. Explain through an example the use of NAT in a network. So we have a detailed video on network address translation. It is used to hide private IP addresses. And so that it can remove the private IP address, put a public IP address, and send the packet out on the internet, and store that information in a table. So when the response comes back, it looks at the table and sees, okay, this packet had come from this private host. Let me now remove my public IP address, which is in the source, which is in the destination IP right now. because the source would be like Google or something or Facebook. And then I'll put the private IP address by looking at the table and send it into my network so that it goes to the correct private host. There are different ways of doing this. I'll not go into the details of that in this video to keep it short. You can go take a look at the NAT video that I have to know more about how it works. I have explained that in a great amount of detail there. What would be the type for the resource record that contains the canonical host name for a host? CNAME. It's right there in the question. Section B. How does TCP determine the timeout for implicit detection of packet loss? Be brief. To know more about how to answer that question, you can read this section from the transport layer chapter in the book of how RTT is calculated, and it's quite involved. And if you're interested, you can go read this, but I'd suggest just skip it for the exam at this point of time. You can learn the Khan's algorithm and all that stuff, but this is out of your syllabus, and I do not recommend you break your head over learning this at this point of time. If it does appear in the exam, you can choose to skip it because this is optional, and I believe it is going to remain that way in the exam. Okay. Sketch the flow of a typical email from Alice to Bob. Assume that Alice and Bob are on different networks. Identify the key components. So you can have the mail user agent, the mail transfer agent, right? MTA, MUA, mail access agents, and whatnot. And the two servers like Yahoo and Google. The way I explained it to you in the email video, you can go take a look at that. And this is a question which keeps coming in all the exams most of the time. So at this point of time, you should know how to answer this. A router has the following CIDR entries in its routing table. So, okay, I can see a problem here. The /23 here should be at the top, but it has got nothing in common with the first two entries, so we should be fine. I mean, there is enough distinguishing prefixes. This is 135, this is 192. So yeah, it can be here, but ideally we should, as a rule, put all the longer prefixes at the top. Okay, so this is the routing table. For each of the following IP addresses, what does the router do if a packet with the address arrives? This address 135.46.63.10. So I'm not going to solve it for all of this. There is a numerical that I have solved, right? It's the network layer activity video. You can go take a look at that. There is a similar problem like this. All you have to do is take this IP, convert this IP address into its binary form, and AND it with all of these masks. So create a /22 mask, so which will have 22 ones on the left and then 10 zeros on the right, and you AND your binary representation of this IP address here in bit A with the mask. And whatever you get, if that matches 135.46.56.0, well, then you send it out of interface 0. If it matches the second line, interface 1, third line, you send it to router 1, and if it doesn't match anything, you send it to router 2. And you do the same thing for all of these other IP addresses too. Consider sending a packet from a source host to a destination host over a fixed route. List and explain the delay components in the end-to-end delay. Which of these delays are constant, which are variable? So we have transmission delay, right? The time it takes for the packet to be put on the connection. We have propagation delay for the head of the message, that engine of the train to be able to go from the origin to the destination, right? Or if the packet is very, very small, the time it takes for the small packet to go from the source to destination is the propagation delay. Then we have queuing delay. You can have queues at the routers and at the end host. And you can also have processing delays, the time it takes for the packet to go through the different layers of the TCP IP stack, right? And out of this, I think only the propagation delay should mostly be a constant because it depends on the physical medium of how fast things can go on that medium. But transmission delay depends on the size of the frame, queuing delay depends on how busy the routers are, and processing delay also depends on the size of the packet you are sending. So these things are not constants. Propagation delay is. Explain why the size of the sender window must be less than 2 to the power m for go back and ARQ. Because if it is exactly equal to 2 to the power m, then what can happen? If you go take a look at the video that I made for go back, and you will see that the receiver can accept a packet it is expecting. The sequence number would be the correct, one, but the packet would be a completely different packet, and that can happen, and the details of that are there in that video. So please go take a look at that. I think you got a similar question in the mid-sem, so you should be careful while answering this question because it's a very, very fundamental question. What is the difference between centralized P2P network and decentralized P2P network? I mean, broadly, in a centralized P2P, there is a server which manages a variety of things, as in where the peers are, what do the peers have, their content, so that if a peer is searching for a certain thing, a certain video or an audio or a document, it can do a search. The search will happen on the server. And the server will then tell you, okay, these are the peers that have it. You can directly go to their locations because the centralized server will tell you, okay, these are the IP addresses of those peers. You can go and talk to them. So that is how centralized P2P networks work. And if the server is gone, well, then the network collapses. It is not going to function well at all at that point of time. So that's a single point of failure, right? In decentralized P2P networks, there is no single point of failure. There is no server as such. All the peers are truly equals and they have distributed information amongst them. So they kind of know as much as possible about the network, or at least what they want from others. They know where those peers are and what those peers have and how much they have. That information is there with these peers, and that is how they communicate with each other and gather information as much as possible. Okay, what is DNS and what is it used for? If all DNS servers could be crashed, taken offline, what would happen to the internet? Well, DNS is the domain name system. And what is it used for? It's used for basically converting a host name to an IP address. And it can do that for IPv4, IPv6, mail exchanger records. It can give you canonical names, aliases. It can give you authoritative name server information using NS records and a bunch of other things. If all the DNS servers crash, then the internet would be fine. Just that name resolutions will not happen. I mean, if you go www.google.com, it won't work. You'd have to remember the IP address of Google and just type https:// IP address of Google. Then you can reach Google, no problem, because you're not depending on DNS at that point of time. But the internet would be fine. Just that humans would have to then start remembering IP addresses, just like we remember phone numbers. What do you mean by congestion control and congestion avoidance? Briefly explain the different congestion control mechanisms used in the network. I mean, congestion control is this broad term. Just like flow control, we do congestion control. Because when you see packets getting dropped because your timer runs out or you get 3 duplicate acknowledgements, you know the packets are not reaching fine until the destination. They're getting dropped somewhere. And that is how you know congestion has happened. And whatever you do to control it comes under congestion control. Congestion avoidance is this entirely different algorithm that we use. It is basically what you do for additive increase, right? So you start with slow start and then you hit the SS threshold. You basically go to congestion avoidance. You do not want to send data so fast that you yourself are creating congestion in the first place. So you're trying to avoid creating more congestion. That is why you avoid congestion, and that is what is congestion avoidance, basically additive increase. Briefly explain the different congestion control mechanisms used in the network. Well, first of all, how do you know congestion has happened? Because if your timer runs out or you get 3 duplicate acknowledgements, and you can then go on to describe Tahoe and Reno using the state diagrams. And just before that, you can write a little bit about how slow start does exponentially increase the congestion window and how additive increase, congestion avoidance, does increase the congestion window linearly. Right? All of that, if you write a little bit briefly, don't make it a very, very long answer, you should be fine. How long does it take a packet of length this much to propagate over a link of distance this much? Propagation speed, transmission rate. Okay, so this is straight out of one of our activities, right? The values might be different. So the size of the packet is given, the bandwidth is given. From that, you can figure out the transmission time. The length of the link is given, the propagation speed is given. From that, you can figure out the propagation delay. You add both of that. Make sure you use consistent units. Okay, don't mix up the units. Kilometers should become meters. 1000 bytes should become bits because the bandwidth is in megabits per second. This M is 10 to the power 6. Okay, not 2 to the power 20. Just keep that in mind. and this speed is fine, meter per second, the standard unit. How long does it take a packet of length L to propagate over a link of distance D, propagation speed S, transmission rate R BPS? So the packet length is L, bandwidth is R, so the propagation delay is L by R. And if the link is of distance D, speed is S, so D by S is the propagation delay. You add both those terms and you get the total delay. Does this delay depend on the packet length? Yes, it does. Because the bigger the packet, the higher the transmission delay. Does this delay depend on the transmission rate? Yes, the higher the transmission rate, the lesser the transmission delay. And the slower the transmission rate, the bigger the transmission delay. Suppose Alice with a web-based email account sends a message to Bob, who accesses his mail from his mail server using POP3. Discuss how the message gets from Alice's host to Bob's host. I mean, it's a pretty similar question than to what you saw here in 2B. So do something very, very similar, right? Just draw that diagram and explain. And it's explained pretty clearly in the email video that I have. After question number 6, let's go to 7. One class B network on the internet has a subnet mask of this. What is the maximum number of hosts per subnet? The subnet mask has how many ones? We have 8, 8, 16 ones. In the 240, we have a 128, we have a 64, and we have, so that would be 128 plus 64 would be 192 plus 32 would be 224 plus 16. So we have 192, 64, 32, 16. So 4 ones are there, right? So we have 8, 8, 4, which is 20. 20 ones are there in the subnet mask. That means 20 ones are required for the network part, the subnet part, leaving 12 bits for the different host addresses. So with 12 bits, you can generate 2 to the power 12 addresses, basically 4096 addresses. So how many hosts will be there? It will be that minus 2, because 2 addresses cannot be used. The first address and the last address in the subnet cannot be used for hosts. So it will be 2 to the power 12 minus 2. Consider a network with 5 nodes, N1 to N5, as shown below. The network uses a distance vector routing. Okay. Once the routes have stabilized, the distance vectors at different nodes are as follows. Okay. Now this is stable. So basically they have sent the distance vectors to their neighbors, and now they have adjusted their distance vectors to be able to figure out the best routes to the different nodes, and the stable distance vectors are given there. N1 is 0, 1, 7, 8, 4, and all the way up to N5 is given. Each distance vector is in the distance of the best known path at that instance to nodes N1 to N5, where the distance to itself is 0. Yeah, that's fine. Also, all links are symmetric and the cost is identical in both directions. That is fine. In each round, all nodes exchange their distance vectors with their respective neighbors. Then all nodes update the distance vectors. In between 2 rounds, any change in cost of a link will cause the 2 incident nodes to change only that entry in their distance vectors. Yeah, all of this is known. This is just trying to tell us the protocol all over again, the algorithm all over again. The cost of link N2, N3 reduces to 2. So N2 to N3, whereas N2 to N3, this is 6, it reduces to 2. So maybe many of these different nodes who actually initially avoided taking that route, now would want to take that route. For example, N4, if it wants to go to N1, what is the cost? N4 to go to N1, the cost is 8. How is that cost 8? Because from N4 to N5 is 4, N5 to N2 is 3, N2 to N1 is 1. So 4 plus 3, 7 plus 1 is 8. But now if this cost N2 to N3 goes to 2, then N4 to N1, there is a better route. It can go through N3 now, because it would be 2 plus 2 plus 1, 5. Right? So these changes will happen. After the next round of update, what will be the new distance vector at node N3? So you basically solve this algorithm, right? So what will happen is that N2 will have a different cost at that point of time. N2 to N3, what is the cost? N2 to N3, 6. This will become a 2 here. And N3 to N2, this 6 will become a 2. So what will happen? N3 will then give some updates to N4, N2. N2 will give updates to N3, N5, N1. So this will all ripple through the network. And it will stabilize again. And you have to figure out what is the distance vector at N3 after this ripple goes through the network. And you can do this. What is the formula to calculate the number of redundancy bits required to correct a bit error in a given number of data bits? So I published a video on Hamming code today. So the formula is, if R is the number of redundant bits and M is the number of bits in the data word, so 2 to the power R should be greater than equal to M plus R plus 1. Okay, so if the number of bits in the data word is 7, then you need R is going to be 4, because 2 to the power 4 is greater than 7 plus 4 plus 1, which is 12. 2 to the power 4 is 16. 16 is greater than equal to 12. That's a formula that you should be using. This question pertains to Hamming code, the video for which I published earlier today. So please take a look at that. Explain an error correction technique on the following data. Data sent is this and data received is this. Well, I can see that a single bit has changed here, 1, and this has kind of changed here. So if you assume that your data word has 4 bits, then 3 bits of redundant bits would be enough for a Hamming code, right? Because 2 to the power 3, which is 8, is greater than equal to 4 plus 3 plus 1, which is 8 again. So if you assume this as the code word, data sent, all of these 7 bits, 4 plus 3 here, then this 1 over here at the left is one of those redundant bits, that is R1, then this 0 over here R2, and then this 1 over here is R4. So these are the 3 redundant bits added. So if you send this and if this is received, then you can recalculate R1, R2 and R4, right? Because you can do the parity the way I showed it in the video. You basically consider this bit, this bit, this bit, this bit, and you figure out the parity. And if it is not 0, whatever it is, you write that. Then you calculate, do it for R2, then you do it for R4, all of those positions, the way I showed it in the video. Then whatever you get by putting R1, R2, R4 together is going to give you the location where the problem is. Basically, it is going to give you 4, right? It is going to tell you that 100 is where the problem is. Okay, 100 is where the problem is, and it will basically pinpoint you to the location where the error has happened, and this 0 here, bit number 4, position 4, has to be flipped from 0 to 1 to be able to get the correct thing intended to be sent there. Why is it that voice and video traffic is often sent over TCP rather than UDP in today's internet? I mean, this question doesn't make a lot of sense. I mean, I'd still say that voice and video traffic still uses UDP in the internet, whether it is today's internet or the internet in the past. But it so happens that because UDP packets are loose packets, I mean, they do not have any particular connection, and the internet usually gets flooded with these packets. So, and these packets can be used to attack a certain server. So firewalls are usually configured to block UDP traffic. They let TCP traffic pass through, but they block UDP traffic. This is the only answer that I can figure out by searching on the internet, at why, because this completely took me by surprise, that why would voice and video traffic, no matter if it's today or yesterday or whenever, it doesn't matter. I mean, they usually use UDP because UDP is used for voice over IP, right? We do not use TCP. I mean, that's the reason we tell students that why is UDP favored over TCP. But it's the only reason I can find is that firewalls block UDP traffic usually, and to circumvent that, to go around that, you use TCP. Thank you.